Welcome. In this lecture, we'll cover normal forms, and in the second part of the lecture, NoSQL databases. Let's start with normal forms. The book says for me, the instructor, to provide an intuitive explanation of normalization. And then we can cover sections 7.1 to 7.3 in a one-semester course. The book is really for a two-semester course, and of course in the second semester we would go over the other sections in chapter 7. So normalization is applied when you're designing a new database structure. It analyzes the relationship among the attributes or fields within each entity or table. It determines if the structure can be improved, and it improves the existing data structure, and it will create an appropriate database design. I'm going to go over an approach recommended by Kent, one of the developers of normalization using functional dependencies, and also one of the developers of the relational database system itself. And he published this in the early 1980s, and it's on our Blackboard class website as a reading. With our intuitive introduction from that paper, and of course this lecture, we'll learn a simple rule to help us do this normalization. Additionally, we will introduce briefly the more complex functional dependencies method used in the book. So data analysis is a technique that's used to improve a data model for implementation as a database. The goal is a simple, non-redundant, flexible, and adaptable database. Normalization is one of the data analysis techniques that helps us organize data in such a way, in other words, into groups to form non-redundant, stable, flexible, and adaptive entities. So we've discussed several times this semester the nature of the relational model. Data is organized into tables, a set of attributes, and a number of entities with those attributes. It has a strict record format. Every record has the same fields, and there are no duplicates allowed. And of course, it's organized into a tabular format. We also discussed the importance of organizing tables into themes. Each table is about one entity, not about multiple entities. An entity is something defined by one theme: student, instructor, department. We get problems when we have a universal table with all the fields in that one table. So take, for example, this slide where we've got a combination of instructor and department themes in one table. What are some of the problems? Well, there's duplicate data. The department data is duplicated for every instructor in that department. We also have modification anomalies. Let's say Mozart leaves and takes a job at another university. If we delete the Mozart record, we lose all the information about the music department as well. And we may not want that. We may plan to hire someone else. What if the computer science department changes from Taylor to Habrowski Hall? We have to be changing that in multiple places, not one place. And if we have some flaw in our logic where we miss some, we get inconsistent data. So we need to consider breaking our universal table into a set of tables that's organized better so we avoid these types of problems. Entity relationship diagrams are one approach and a good start. They are for more of a conceptual design, one that we show the customer. How we go about analyzing each table we have from our entity relationship process is more involved, and one of the techniques we can use to do that is normalization. So if we look at that jumbo table with both instructor and department, we can see that department name determines uniquely the department building and the department budget. These are department characteristics. That is to say that building and budget are functionally dependent on department name. So they are really a hidden table inside that jumbo table of instructor and department. So functional dependence, more formally, is the attribute B is fully functionally dependent on attribute A if each value of A determines one and only one value of B. So normalization is evaluating and correcting table structures to minimize data redundancies, reduce data modification anomalies, align attributes to tables based on functional determination. There's 3 normal forms that we'll consider in our course. And in fact, most businesses only consider these 3 normal forms. They go to the 3rd normal form usually. And sometimes they'll even back off that if they have performance problems. And we'll get into why there's performance problems the more tables you get and the more joins you have to do therefore. So the higher the normal forms, the better the design is considered to be. Denormalization is a process that produces a lower normal form from a higher normal form, and it results in increased performance because we don't have to do join operations. But we introduce data redundancy and the potential for those modification anomalies. The footnote in this slide is the article by Kent, 1982, and it's in the American Computing Machinery Journal, Communications. So, simple guide to the 5 normal forms, and it's on our website. The whole idea behind normalization is finding a table hidden within another table. With the normalization process, the objective is to ensure that each table conforms to the concept of a well-formed relation. In other words, each table represents a single subject. No data item will be unnecessarily stored in more than one table. All non-prime attributes in a table are dependent on the primary key. And each table is void of insertion, update, and deletion anomalies. And there's a little ditty that we can remember to help us do that. Every non-key attribute in a table is dependent on the key, the whole key, and nothing but the key. And in the rest of the lecture on normalization, we'll see how we go about doing that. So first normal form is an entity whose attributes have no more than one value for a single instance of that entity. Any attributes that can have multiple values actually describe a second entity, and possibly an entity and a relationship both. A second normal form is an entity whose non-primary key attributes are dependent on the full primary key. This comes into play when we have a primary key composed of more than one attribute. So if some of the non-key attributes are dependent on only part of that composite primary key, we're in violation of second normal form. So any non-key attributes dependent on only part of the primary key should be moved to a separate table or separate entity where the partial key is the primary key. And this may require creating a new table and relationship on the model. Third normal form is an entity whose non-primary key attributes are not dependent on any other non-key attributes. So any non-key attributes that are determined by another non-key attribute must be moved to a separate table or deleted if they're not really necessary. And again, we need to look at adding tables and relationships to our model to accomplish getting rid of these problems. The normalization process ensures that all tables are at least in third normal form. Higher forms are not likely to be encountered in the business environment. We start by identifying the dependencies in a table or relation, and then progressively breaking the table or relation into a set of new tables or relations. We start with getting our tables into first normal form. That's a table format with no repeating groups, and you have a primary key. So one candidate that always comes up that violates the first normal form would be something like phone numbers. So instructor has phone number field, and that could have cell phone, work phone, and home phone. First normal form is the starting point to then go to second normal form. And that's where, again, there's no partial dependencies. In other words, parts of some of the attributes in the database are dependent on part of the key. That's a partial dependency, and that's a violation of second normal form. And then we start in second normal form, and we can go to third normal form by ensuring there's no transitive dependencies. That's where a field is dependent on another non-key field. So first normal form describes a tabular format in which all key attributes are defined. There's no repeating groups in the table like phones, and all attributes are dependent on the primary key. All relational tables satisfy first normal form requirements. So essentially, getting your design into first normal form is actually making it compliant with the relational model. Once you do have it in first normal form, then it's possible that you may have some of these other problems, partial dependencies and transitive dependencies. So here's a very common problem. Phones are a multi-valued attribute, and we cannot handle these in relational tables. So in our design on the top, we see we have an attribute called telephone number, and in it, we may have multiple telephone numbers. So with first normal form violation, we have our first indicator that we have a table hidden in another table. The multi-valued attributes are that indicator. And we see that when we go through a decomposition. A decomposition is where we take the offending field or fields out of the table they're in and put them into a separate table with a key that we can use to look up values or do joins with from the original table. So in this particular case, we might take our telephones and put them into a separate table where each telephone number has its own record, rather than having multiple telephone numbers in one field in one record. We have one telephone number in one field, but in multiple records. We carry over the customer ID so that we can do a join or a lookup from customer name to customer telephone number, and we assign a primary key to our new table. A repeating group is a group of multiple entries of the same type that can exist for any single key occurrence. The existence of this proves the presence of data redundancies and the potential for anomalies. So the steps we go about doing a normalization are first eliminate the repeating groups. We identify the primary key, then we remove the fields that have repeating groups and put them into a separate table with a key that we can use to join them to the original table. So we take them out of the original table and put them in their own table, and then put key in the new table so that we can join it back if we need to. There are times when we want to get an instructor's phone number. So second normal form is where we make sure there are no partial dependencies. The steps we go through, we make new tables to eliminate partial dependencies, and we reassign corresponding dependent attributes to those tables. A table is in second normal form when it is first in first normal form, and secondly, it includes no partial dependencies. And remember, a partial dependency is where a non-key attribute is dependent on only one part of a multi-field primary key. Second normal form comes into play when we have a composite primary key. In our ditty, it's the whole key. Every non-key field is dependent on the whole key. If one or some of the non-key attributes is dependent on only part of the composite key, then that is a hidden table that needs to be made into its own table. So, thinking about a bank database, we have a table called accounts, and a customer can have different types of accounts, checking and saving, for example. So in this particular table, we see on slide 14, the primary key is customer ID and account number. So when we look at it, we see that balance is determined by account number alone and not by customer ID. And likewise, customer name is determined only by customer ID and not account number. Such a partial key dependency violates second normal form. So we can look at what might happen when we update things. What happens if we need to update the balance in C001, or if Ray G changes his name, or what if Masters closes account S002 but is still considered a customer because they have loans? So there's redundancy also. Name is repeated for every account. Ray G is up there twice, once for the savings account and once for the checking account. So again, we've got the potential for anomalies. We correct the problems by decomposing. We take the offending fields out and put them into their own table. For example, since balance is determined completely by account ID, we put those into their own table. And let's call that the account table. And we have our savings accounts and our checking accounts in there. Likewise, a customer name is determined by customer ID. So let's put them into a customer table. And then the original table now has only two fields, customer ID and account number, and we can rename that depositor table. So the customer can be a depositor, and we don't show this here, but the customer can also be a borrower and have loans and have a loan table. So it gives us more adaptability also, breaking it down like this. And now for the final phrase in our ditty, and nothing but the key. So every non-key attribute must be determined only by the key and not by any non-key fields. So to correct the problem, we make a new table to eliminate such transitive dependencies. Keep in mind, a determinant is any attribute whose value determines other values within a row. A table is in third normal form when it starts off in second normal form, and we determine that it has no transitive dependencies. So here's an example of a table that violates third normal form. We'll say that a campus is only in one city, and that seems to be a reasonable premise. So the non-key attribute city in this table is a fact about another non-key attribute branch. So a campus or a branch is only in one city. So if you know the campus or the branch, you know the city. Likewise, if you know the employee ID, which is the key field, that uniquely determines the branch and the city in a particular record. Now, employee ID is a unique identifier. So again, it uniquely points to the record, and the city is determined by the employee ID. But the city is also determined solely by branch. If you know the branch, which is a non-key field, that determines the city, which is a non-key field. This is a transitive dependency. So this leads to, again, some problems. If a branch moves out of one city into another, then all the records for that duplicated city must be updated. A branch city is repeated for every employee assigned to that branch, so we have redundancy. And with redundancy, there's a risk of inconsistency over time. So this has some problems that we want to get rid of. We get rid of those by going through our process of decomposing, removing the offending fields and putting them into their own tables, and then having a key that lets us connect back to the original table. So we take city out of our employee table and we put it in a table called branch table. We use branch, which is the determinant of city in the original table. That becomes the primary key in the branch table. And then we can join employee table and branch table on the branch field. So in summary, we evaluate primary key assignments and naming conventions. We look at atomicity. We cannot have multiple fields, multi-valued fields. We identify the new attributes and new relationships. And then with the primary keys, we look for every non-key attribute must be dependent on the key, the whole key, and nothing but the key. Okay, now let's get into functional dependencies, which are a little more complex than the intuitive approach we just looked at. However, if you remember that ditty, every non-key attribute is dependent on the key, the whole key, and nothing but the key, you'll be able to do normalization to the third normal form. So, again, in sections 7.1 through 7.3, the book introduces this concept of functional dependencies. One important characteristic is that a functional dependency is based on facts that have a unique singular identifier. For example, we might say that a person determines a business address if everyone has the same business address. A functional dependency if the person has a unique identifier like social security number, that person would determine, for example, the department, Sherman Hall at UMBC. Another social security number might determine another department, McKeldin Library at University of Maryland College Park. So we're looking at facts that can be uniquely identified and determine the value of other attributes as functional dependencies. So here's the notation we use for that functional dependency. We say that X functionally determines Y, and we denote that with X arrow pointing to Y. The left side attributes, X in this case, are called determinants. So we can also say that X arrow Y, you can read that as X determines Y. And that means once we know a value for X, we know the value for Y. It has to be one thing only once we know the value of X. So our normalization process, first thing we do is we identify the key. And we've learned all along in the course that there's an extreme importance attached to the primary key. Then we look for functional dependencies. We analyze the table row and we test the relation against each normal form. And again, are there multi-valued attributes? Is it a composite key and some of the attributes are determined by part of that key? Or is it a transitive dependency where we have a non-key attribute determining another non-key attribute? If it fails to satisfy a normal form, then we go through our decomposition. We take the offending fields out, we put them in their own table. We keep going through this iteratively until we've got all our tables in the normal form we want, usually third normal form. And then in business, you might back that off to less than third normal form for performance reasons. So with that, let's take an example. So we'll go through this. This is a university all-in-one table up in the top part. And I just call it all-in-one table. And you can see that it's got a lot, a lot of the fields we had in our university schema. Obviously not the buildings and the ancillary things, but the main core elements we have all in one table. When we talk with our users, we learned that we have these functional dependencies. Student ID determines the name and total credits. Student ID, course ID, and PeopleSoft section ID determine the grade. Course ID determines the course name. And the faculty ID determines the professor's name and salary. Faculty ID, course ID, and PeopleSoft section ID determine the rating. And then PeopleSoft ID and course ID determine the semester and the year. So, given our intuitive guidelines for third normal form, that a non-key attribute is about the key, the whole key, and nothing but the key, consider this schema and let's decompose it. So let's go through this, and we'll start by just taking one of the functional dependencies at a time out of the table. So here we are, the first step. We've taken our all-in-one table and we've looked at the functional dependencies. And I started with functional dependency 6, where the PeopleSoft section ID determines, along with the class ID, the semester and the year. So we create a separate table with those fields in it. We take semester and year out of the all-in-one table, and then we are left with 5 functional dependencies that we have to deal with. And these are, of course, now we've already taken care of the PeopleSoft class ID and course ID determine semester and year. Now we still have left student ID determines name and total credits, and student ID and the PeopleSoft section ID determine grades taken for a course. And then the course ID determines the course name, faculty ID determines the professor name and salary, and then faculty ID and PeopleSoft section ID determine the rating for the course's top. So we're going to continue decomposing the one large table into sets of tables that are finally in third normal form. So let's go to step 2. The all-in-one table, we've now applied functional dependency 1, and we end up with 3 tables now. The original table keeps getting smaller, and now we have a student table along with our PeopleSoft class table. Next, we get rid of functional dependency 4, creating a faculty table. And notice that our all-in-one table, again, continually gets smaller and smaller as we remove the offending fields with functional dependencies. And notice how we are leaving keys into the original table so that we can link them together and join all the tables into the, join the original table with the new tables that we're creating. Okay, and then in step 4, we get rid of functional dependency 3 and create a course table. And again, we get rid of the offending fields, and we're ready to go on to step 5. Here in step 5, we get rid of functional dependency 2 and create the table takes. And now we're left with one final functional dependency that we've got to take care of. And that we do by creating the teaches table. And now we've decomposed and we have a set of tables that we can use. The original all-in-one table, we may keep it around, but it may be redundant in the relations we just created because it has no non-key fields, but we'll make a determination whether we want to keep the original stub around or not. But we, in fact, now have satisfied all the functional dependencies against that all-in-one table. And we have a set of tables: class or course, student, faculty, course name. This is section up here, PS, class, section, student, faculty, course, takes, and teaches. Okay, let's take a 10-minute break. And then when we come back, we'll go over relational databases.